At the end of the 19th century, physics stood at a strange crossroads. To the outside world, it appeared complete, elegant, and nearly perfect. The laws formulated by Isaac Newton had ruled scientific thought for more than 2 centuries, accurately predicting the motion of planets, the fall of objects, and the mechanics of machines. James Clerk Maxwell's equations had unified electricity, magnetism, and light into a single, powerful framework. Many leading scientists believed that nature's deepest secrets had already been uncovered, and that future work would consist only of refining measurements to a few more decimal places. Yet beneath this surface of confidence, a quiet crisis was growing, one that classical physics could not resolve. This crisis did not arrive suddenly or dramatically. It emerged slowly, through small experimental discrepancies that refused to disappear. Precision measurements, made possible by improved instruments, began to reveal cracks in the classical world. These were not errors caused by poor equipment or careless experimentation. They were systematic, repeatable failures of theory itself. Classical physics, which treated energy as continuous and predictable, began to struggle when applied to phenomena involving heat, radiation, and matter at very small scales. One of the most troubling issues came from the study of thermal radiation. When objects are heated, they emit electromagnetic radiation. This radiation changes in color and intensity depending on temperature, a phenomenon easily observed when metal glows red, then white, as it becomes hotter. Physicists attempted to explain this behavior using classical theories of energy and electromagnetism. Early formulas worked well at low frequencies, but failed badly at higher ones. According to classical predictions, a hot object should emit infinite energy at high frequencies, a result that was not only incorrect but physically impossible. This failure became known as the ultraviolet catastrophe, a term that captured both the mathematical absurdity and the looming collapse of classical explanation. The ultraviolet catastrophe was not merely a technical inconvenience. It represented a fundamental contradiction between theory and reality. If classical physics were correct, the universe itself would be unstable, constantly emitting infinite energy. Since this clearly did not happen, something was deeply wrong. Scientists tried to fix the problem by adjusting equations, adding assumptions, and refining models, but nothing worked. The more they experimented, the clearer it became that classical physics was reaching the limits of its explanatory power. At the same time, other anomalies began to surface. The behavior of gases at very low temperatures deviated from classical predictions. The distribution of energy among molecules did not match theoretical expectations. Spectral lines emitted by atoms appeared at precise frequencies rather than forming smooth, continuous patterns. These observations suggested that energy might behave in a discrete way, but such an idea clashed violently with classical thinking. Continuity was a sacred principle of 19th century physics, deeply embedded in both mathematics and philosophy. Despite these warning signs, many physicists resisted the idea that a radical change was necessary. Classical physics had proven itself countless times and had led to enormous technological progress. Railways, telegraphs, engines, and electrical systems all relied on its principles. To question its foundations felt almost unthinkable. Instead, scientists hoped that the troubling results were temporary gaps that future refinements would fix. The prevailing attitude was one of cautious optimism mixed with denial. This resistance was not rooted in stubbornness alone, it was philosophical. Classical physics was built on determinism, the belief that the future behavior of a system could be predicted exactly if its present state were known. Nature, according to this view, was orderly and continuous. Randomness and discreteness were signs of ignorance, not fundamental properties of reality. Any suggestion that nature might operate in jumps rather than smooth flows was deeply unsettling. As experimental data accumulated, the pressure on classical theory increased. Laboratories across Europe were producing results that refused to fit established laws. Physicists found themselves in a paradoxical situation. Their equations were mathematically beautiful and logically consistent, yet they failed to describe the real world in crucial cases. The crisis was no longer hidden. It was openly discussed in scientific circles, yet no one knew how to escape it. It was within this tense intellectual atmosphere that Max Planck began his work. He was not driven by a desire to overthrow classical physics, but by a determination to preserve it. Planck believed strongly in absolute physical laws and regarded entropy and thermodynamics as fundamental truths. When he confronted the problem of blackbody radiation, he approached it as a conservative thinker, seeking a solution that would restore harmony between theory and experiment without altering the foundations of physics. Planck's struggle illustrates the depth of the crisis. For years, he tried to derive a formula using classical assumptions, only to fail repeatedly. Each attempt revealed the same contradiction. Continuity simply did not match observation. Finally, in an act of intellectual desperation, Planck introduced an assumption that energy could be emitted only in finite, discrete amounts. This idea was not meant to describe reality as such. It was a mathematical compromise, a tool to make the equations work. Yet this compromise would soon become the seed of a revolution. The crisis of classical physics at the end of the 19th century was therefore not just a scientific problem, but a turning point in human thought. It marked the moment when long-held assumptions about nature began to crumble under the weight of evidence. The failure to explain heat radiation exposed the limits of determinism and continuity, forcing physicists to confront the possibility that reality operates according to principles far stranger than previously imagined. In retrospect, the crisis appears inevitable. As science pushed deeper into the microscopic world, the tools of classical physics were bound to fail. They had been designed to describe everyday objects and large-scale phenomena, not atoms and energy exchanges at the smallest scales. Yet at the time, this realization was far from obvious. It required courage, humility, and a willingness to abandon comfort in favor of truth. This unresolved tension between theory and experiment set the stage for the quantum revolution. The classical world did not collapse overnight. It resisted, adapted, and fought back. But the crisis at the end of the 19th century made one thing clear. Physics could no longer remain the same. A new framework was needed, one capable of explaining the strange and fragmented behavior of the microscopic world. The silent pressure of this crisis would soon give rise to ideas that transformed science forever. As the 19th century drew to a close, the crisis within classical physics deepened, even though many outside the scientific community remained unaware of it. Physics textbooks still presented the universe as a perfectly predictable machine, governed by smooth equations and timeless laws. Yet in research laboratories, confidence was steadily eroding. Each new experiment brought results that classical theories could not fully explain. Instead of clarity, physicists encountered contradictions that grew more difficult to ignore. One of the most unsettling aspects of this crisis was that it emerged not from speculative theory, but from careful measurement. Experimental physics had entered an age of precision. Instruments became sensitive enough to detect subtle deviations that earlier scientists could not observe. What once appeared continuous now revealed structure. What once seemed smooth now appeared irregular. Classical physics, which had thrived on approximation and idealization, began to fail under the demand for exactness. Thermodynamics played a central role in exposing these weaknesses. The laws of thermodynamics were firmly established and experimentally verified, yet their deeper meaning remained unclear. Entropy, in particular, raised troubling questions. It described the direction of natural processes, the irreversible flow of time, and the tendency toward disorder. Classical mechanics, however, was time, reversible. Its equations made no distinction between past and future. This contradiction suggested that something fundamental was missing from the classical picture. The conflict between thermodynamics and mechanics became impossible to ignore. If microscopic particles obeyed deterministic laws, how could macroscopic systems display irreversible behavior? Attempts to reconcile the two relied on probability and statistics, but these methods felt like philosophical compromises rather than true explanations. They worked mathematically, yet they hinted that certainty was being replaced by likelihood, and exact prediction by averages. For many physicists, this shift was deeply uncomfortable. Radiation theory intensified the sense of crisis. When physicists tried to describe how energy was distributed among electromagnetic waves inside a heated cavity, they encountered results that defied logic. Classical theory predicted that energy would accumulate infinitely at short wavelengths. This was not merely inaccurate. It suggested a universe that could not exist. The fact that experiments consistently contradicted theory forced scientists to confront a painful possibility. The most trusted laws of physics were incomplete. Some physicists proposed that matter itself might be responsible for the discrepancy. Others suggested that the interaction between matter and radiation was not fully understood. Still, others believed that the problem lay in experimental error. Yet as different laboratories reproduced the same results, denial became harder to maintain. The crisis was no longer isolated, it was systemic. The intellectual atmosphere of the time was marked by tension between tradition and necessity. Senior scientists, trained in classical methods, were reluctant to abandon ideas that had served them so well. Younger researchers, less attached to established doctrines, were more willing to explore unconventional possibilities. This generational divide contributed to uncertainty and debate. Physics conferences became arenas of quiet disagreement, where confidence was publicly maintained while doubts were privately acknowledged. Philosophical implications weighed heavily on the scientific community. Classical physics was not just a set of equations, it was a world view. It supported the belief that nature was rational, predictable, and ultimately knowable. Human reason, armed with mathematics, could uncover every secret of the universe. The emerging crisis threatened this belief. If classical laws failed at fundamental levels, then certainty itself was at risk. This unease extended beyond physics into philosophy and culture. The late 19th century was already a time of intellectual upheaval. Traditional beliefs were being challenged in biology, psychology, and social theory. Darwin's theory of evolution had altered humanity's view of itself. Freud's ideas were questioning the stability of the human mind. In this broader context, the crisis in physics seemed part of a larger pattern, the collapse of absolute certainty. Yet, unlike other fields, physics demanded solutions that could be tested and measured. It could not retreat into abstract debate. The equations had to work. The predictions had to match reality. This requirement forced physicists to confront the crisis directly, even when the implications were unsettling. Each failed explanation narrowed the range of acceptable assumptions. The growing sense of limitation led some scientists to adopt a pragmatic attitude. Instead of asking what nature truly was, they focused on what could be calculated and observed. This shift marked a subtle but profound change in scientific thinking. Truth became associated less with intuitive understanding and more with empirical success. If a formula matched experiment, it was accepted, even if its meaning was unclear. This pragmatic approach set the stage for radical innovation. Once continuity, determinism, and classical causality were no longer sacred, new ideas could emerge. The crisis forced physicists to question assumptions that had once seemed obvious. Why must energy be continuous? Why must physical processes be strictly deterministic? Why must observation play a passive role? These questions would have been unthinkable decades earlier, yet now they became unavoidable. The emotional toll of this transition should not be underestimated. Many physicists experienced a sense of loss. The elegant simplicity of classical mechanics was being replaced by fragmented models and provisional explanations. The comfort of certainty gave way to doubt, yet alongside this discomfort grew excitement. The failure of old theories meant that new discoveries were possible. The unknown, once feared, became a source of opportunity. As the crisis intensified, it became clear that no minor adjustment could resolve it. Classical physics was not wrong in general. It remained extraordinarily accurate for large-scale phenomena. But it was incomplete. Its laws described an approximation of reality, not its foundation. This realization marked a turning point. Physics was no longer a finished project, but an evolving framework, capable of transformation. The end of the 19th century thus stands as a moment of profound transition. Classical physics, once regarded as the final word on nature, was revealed to be a powerful but limited description. The anomalies that plagued radiation, thermodynamics, and atomic behavior were not isolated failures. They were signals pointing toward a deeper structure of reality. The crisis did not destroy physics, but it stripped away its illusions of completeness. Out of this uncertainty emerged a willingness to accept ideas that defied intuition. Discreteness, probability, and observer dependence would soon enter the heart of physical theory. These concepts would challenge not only scientific methods, but human understanding itself. The crisis of classical physics was therefore not an ending but a beginning, a necessary breakdown that made transformation possible. By forcing physicists to confront the limits of their knowledge, the crisis opened the door to a new vision of the universe. It taught that nature is not obligated to conform to human expectations, no matter how reasonable they seem. Instead, understanding must follow evidence, even when it leads into unfamiliar territory. This lesson, learned at the close of the 19th century, became the foundation upon which the quantum revolution would soon rise. Max Planck's scientific mindset was shaped long before he became associated with the quantum revolution. He grew up in an academic environment where respect for tradition, discipline, and intellectual rigor were deeply ingrained. From the very beginning of his career, Planck believed that the laws of nature were absolute and unchanging. To him, physics was not a field meant for speculation or philosophical rebellion, but a serious pursuit aimed at uncovering eternal truths that already existed, waiting patiently to be revealed through careful reasoning and precise mathematics. During the late 19th century, when Planck entered the world of professional physics, classical theory was regarded as one of humanity's greatest intellectual achievements. Newtonian mechanics and Maxwell's electromagnetic theory formed a harmonious picture of the universe. Nature appeared continuous, deterministic, and orderly. Planck embraced this world view completely. Unlike some of his contemporaries who enjoyed bold hypotheses and imaginative leaps, he valued certainty and logical consistency above all else. He distrusted ideas that relied too heavily on approximation or probability, viewing them as signs of incomplete understanding rather than fundamental truths. Planck's conservatism was not merely personal preference, it was philosophical. He believed that physical laws existed independently of human observation. In his view, nature did not change its behavior based on how it was measured or interpreted. The task of the physicist was to discover these laws, not invent them. This belief placed him firmly within the classical tradition and made him deeply skeptical of any suggestion that physics required radical revision. This cautious mindset influenced his early research choices. At a time when many physicists were drawn to electromagnetism or experimental work, Planck focused on thermodynamics, particularly the concept of entropy. He considered the second law of thermodynamics to be a fundamental principle of nature, not a statistical rule derived from probability. This position put him at odds with scientists like Ludwig Boltzmann, who interpreted entropy in terms of atomic motion and probability. Planck resisted Boltzmann's ideas for years, believing that reliance on statistics undermined the certainty physics should strive for. Planck's resistance to probabilistic thinking reveals much about his character. He sought certainty in a world that increasingly pointed toward uncertainty. While others were willing to accept that microscopic processes might behave unpredictably, Planck held firmly to the idea that randomness reflected ignorance, not reality. To him, nature followed strict laws, even if humans had not yet discovered them. This conviction made him cautious, methodical, and deeply uncomfortable with speculative explanations. When experimental results began to challenge classical physics, Planck did not immediately welcome the disruption. Instead, he viewed anomalies as temporary problems that would eventually be resolved within the existing framework. This attitude was common among physicists of his generation, but Planck embodied it with particular intensity. He believed that the beauty and success of classical physics could not be accidental, and that abandoning it would mean abandoning centuries of intellectual progress. This conservative approach became especially evident when Planck confronted the problem of Blackbody radiation. Rather than searching for revolutionary ideas, he attempted repeatedly to derive a solution using classical principles. Each failed attempt strengthened his determination rather than weakening it. He believed that persistence, not radical thinking, would ultimately restore order. For Planck, the idea that nature might behave discontinuously was not just strange, it was almost unacceptable. What makes Planck's story remarkable is that the very person least inclined toward revolution became the one who initiated it. His cautious mindset did not make him blind to evidence, however. While he resisted radical interpretation, he respected empirical results deeply. When experiments consistently contradicted theory, Planck did not dismiss them. Instead, he experienced an intense internal conflict between his philosophical beliefs and the undeniable reality of data. This conflict reached its peak when Planck introduced the assumption that energy could be exchanged only in discrete amounts. It is important to understand that he did not view this as a description of physical reality. He saw it as a formal device, a mathematical trick designed to make equations match observations. In his mind, it was a temporary step, one that future theories would eventually eliminate. His conservatism allowed him to accept the assumption only because he believed it did not fundamentally alter the nature of physical law. Planck's cautious personality shaped how he presented his work to the scientific community. He did not proclaim the end of classical physics or announce a new era. Instead, he introduced his findings with restraint and humility. He emphasized the empirical success of his formula while downplaying its conceptual implications. This careful presentation reflected his desire to minimize disruption and maintain continuity with established theory. The scientific community initially responded in kind. Many physicists viewed Planck's work as a clever solution to a specific problem rather than a fundamental breakthrough. This response aligned with Planck's own interpretation and delayed the recognition of quantum theory's revolutionary nature. Ironically, his conservative framing may have helped his idea gain acceptance, as it did not appear to threaten the foundations of physics outright. Despite this, Planck himself struggled internally. As others began to extend his ideas in bold and unexpected directions, he watched with a mixture of admiration and unease. Albert Einstein's explanation of the photoelectric effect, which treated light itself as quantized, pushed Planck's assumption far beyond what he was comfortable with. Yet even then, he did not publicly oppose Einstein. His respect for intellectual honesty prevented him from rejecting ideas that were supported by evidence, even when they conflicted with his beliefs. Planck's cautious mindset also influenced his role as a teacher and academic leader. He valued discipline, patience, and respect for tradition in his students. He did not encourage speculation for its own sake, but emphasized careful reasoning and mathematical rigor. This approach shaped a generation of physicists who, even as they developed quantum theory further, inherited Planck's respect for evidence and logical structure. Over time, Planck came to accept that the implications of his work could not be ignored. Classical physics, while still valid in many contexts, was not the ultimate description of nature. This realization did not bring him joy or excitement. Instead, it brought a sense of solemn acceptance. He recognized that science advances not according to human preference, but according to truth revealed through observation. Planck's conservatism gives his contribution a unique significance. He did not seek to overthrow established ideas, yet he possessed the intellectual integrity to follow evidence wherever it led. This combination of caution and honesty allowed him to bridge two eras of physics. He stood with one foot firmly planted in the classical world, and the other stepping reluctantly into the quantum age. His story challenges the popular image of scientific revolutionaries as bold rebels. Planck shows that revolutions can also be born from restraint, discipline, and respect for tradition. His cautious mindset did not prevent progress. Instead, it ensured that progress was grounded in evidence rather than speculation. By refusing to ignore experimental reality, even when it contradicted his deepest beliefs, Planck demonstrated the highest ideal of scientific integrity. In the end, Max Planck did not abandon his belief in absolute laws. He refined it. He came to understand that the laws of nature were more subtle and complex than classical physics had suggested. They were not less real, but less intuitive. This acceptance marked a quiet transformation within Planck himself, mirroring the larger transformation of physics as a whole. The irony of Planck's legacy lies in the contrast between his personality and his impact. A cautious, conservative thinker became the founder of a theory that shattered classical certainty and reshaped human understanding of reality. His mindset reminds us that true scientific progress does not require a desire to revolutionize, but a commitment to truth strong enough to withstand the collapse of even the most cherished beliefs. As the implications of Planck's work slowly began to unfold, his cautious and conservative mindset became even more visible in how he reacted to the emerging quantum ideas. While younger physicists embraced novelty with enthusiasm, Planck remained reserved, almost hesitant, as if watching a force he had unintentionally released. He never denied the success of quantum-based explanations, but he struggled to accept their philosophical meaning. For him, physics was still rooted in objective reality, not in probabilities or observer-dependent outcomes. This inner tension defined much of Planck's later intellectual life. On one hand, he recognized that his radiation law worked flawlessly where classical theories failed. On the other, he remained emotionally and philosophically attached to determinism. He hoped that quantum assumptions were provisional tools rather than permanent features of nature. This hope shaped his public statements, which often emphasized continuity rather than rupture. He preferred to speak of refinement and extension instead of revolution. Planck's conservatism also influenced how he viewed the role of mathematics in physics. He believed mathematical form should reflect physical truth, not merely fit experimental data. This belief made him uneasy with approaches that prioritized predictive success over conceptual clarity. As quantum theory evolved, mathematical formalisms became increasingly abstract, relying on probability amplitudes and wave functions rather than concrete physical pictures. Planck respected the mathematical achievements, but remained uncomfortable with their interpretation. Unlike some of his successors, Planck did not delight in paradox. He did not celebrate uncertainty as a fundamental principle. Instead, he saw it as a sign that understanding was incomplete. While Heisenberg's uncertainty, principle, and Bohr's complementarity fascinated the scientific community, Planck regarded them with restraint. He accepted them as empirically valid, but resisted the idea that they represented the final word on nature. In his view, deeper laws might one day restore clarity and determinism at a more fundamental level. This attitude reflected Planck's lifelong belief in the independence of physical laws from human perception. He rejected the notion that observation played a creative role in shaping reality. To him, measurements revealed nature but did not define it. This position placed him at odds with interpretations of quantum mechanics that emphasized the observer's role. While he did not engage in public philosophical battles, his writings consistently expressed concern about subjectivism entering physics. Planck's cautious stance also shaped his interactions with other scientists. He supported innovative thinkers when their work was grounded in evidence, even if he disagreed with their interpretations. His early support of Einstein is a clear example. Although Einstein's ideas pushed quantization far beyond what Planck initially intended, Planck recognized their explanatory power and defended Einstein's work when it faced skepticism. This support demonstrated that Planck's conservatism did not translate into close-mindedness. At the same time, Planck's restraint sometimes limited his engagement with the deeper implications of quantum theory. While others debated interpretation passionately, Planck often stepped back, focusing instead on broader questions about the nature of scientific progress. He believed that revolutions in science should be approached with humility, not triumphalism. For him, the collapse of classical certainty was not a victory, but a reminder of human limitation. This humility became more pronounced as Planck aged. He witnessed physics undergo transformations that few could have imagined at the beginning of his career. Relativity altered concepts of space and time, while quantum mechanics challenged causality and realism. Through all this, Planck maintained a steady demeanor. He neither resisted change outright nor embraced it uncritically. His response was reflective rather than reactive. Planck's personal experiences also reinforced his conservative outlook. Living through periods of political upheaval and personal tragedy, he came to value stability and order deeply. These values influenced his scientific philosophy. He sought permanence in physical law as a counterbalance to uncertainty in human affairs. This search for order made the probabilistic nature of quantum mechanics particularly unsettling to him, even as he acknowledged its necessity. Despite his reservations, Planck gradually accepted that quantum ideas were not temporary fixes, but essential components of physical theory. This acceptance did not come with excitement or relief, but with a sense of responsibility. He understood that science must follow evidence, regardless of personal preference. This willingness to yield to reality, even reluctantly, defined the integrity of his character. Planck's cautious mind set also shaped how history remembers him. Unlike more flamboyant figures, he did not leave behind dramatic declarations or philosophical manifestos. His influence is quieter, embedded in equations, constants, and institutional support for emerging ideas. Yet this quiet influence proved decisive. By lending his authority to early quantum research, he helped legitimize a field that might otherwise have faced greater resistance. In educational settings, Planck continued to emphasize discipline and respect for established knowledge. He believed that innovation should grow from mastery of tradition, not rejection of it. This belief influenced how quantum theory was taught in its early years, grounding revolutionary concepts in rigorous mathematical training. Even as physics transformed, Planck's values ensured continuity in scientific culture. The contrast between Planck's personality and the consequences of his work highlights a deeper truth about scientific progress. Breakthroughs do not always arise from bold rebellion. Sometimes they emerge from careful, conservative efforts to resolve specific problems. Planck's reluctance to abandon classical physics forced him to explore its limits thoroughly. In doing so, he revealed where those limits truly lay. His story also illustrates the emotional complexity of discovery. Scientific advances are often portrayed as moments of triumph, but for Planck, discovery came with discomfort. Each step away from classical certainty felt like a loss, yet he accepted that loss as the price of honesty. This acceptance gave his contribution a moral dimension, showing that progress requires not only intelligence, but courage of a quieter kind. Planck's conservative mindset ultimately served as a bridge between eras. He spoke the language of classical physics fluently while introducing ideas that pointed beyond it. This dual role allowed quantum theory to emerge gradually rather than explosively. By framing his assumption as modest and technical, he reduced resistance and allowed others to explore its implications more freely. In time, Planck recognized that the value of a scientific theory lies not in its comfort, but in its truth. This realization did not erase his longing for determinism, but it tempered it with realism. He came to see uncertainty not as chaos, but as a deeper order that had yet to be fully understood. This perspective allowed him to reconcile, at least partially, his classical instincts with quantum reality. The legacy of Planck's cautious and conservative mind set is therefore not one of obstruction, but of balance. His restraint prevented reckless speculation, while his honesty prevented denial. He demonstrated that one can honor tradition without being enslaved by it, and embrace change without celebrating confusion. In this balance lies his true genius. Max Planck did not set out to redefine physics. yet his careful adherence to evidence forced him to do exactly that. His mindset reminds us that scientific revolutions need not begin with defiance. They can begin with loyalty to truth, to rigor, and to the responsibility of following nature wherever it leads, even when the path is uncertain. The Blackbody radiation problem emerged as one of the most puzzling scientific challenges at the end of the 19th century, quietly exposing the limitations of classical physics. A blackbody refers to an idealized object that absorbs all incoming radiation and emits energy solely based on its temperature. While this concept sounds abstract, it closely matches real physical systems, such as heated metals or stars. Understanding how a blackbody emits radiation was not just an academic exercise. It was essential for explaining light, heat, and the fundamental interaction between matter and energy. When an object is heated, it begins to glow. As the temperature rises, the color of the emitted light shifts from red to orange, then to white and blue. Scientists carefully measured this radiation and discovered a precise pattern in how energy was distributed across different wavelengths. These measurements were remarkably consistent, suggesting that nature followed a strict and universal rule. The challenge was to explain this rule using existing physical theories. Classical physics approached the problem using well-established principles of electromagnetism and thermodynamics. According to these theories, energy inside a heated cavity should be shared equally among all possible electromagnetic waves. This assumption worked well for long wavelengths, where predictions closely matched experimental results. However, at shorter wavelengths, classical theory produced increasingly inaccurate results. The equations suggested that as wavelength decreased, the amount of emitted energy should increase without limit. This prediction led to a deeply troubling conclusion. If classical theory were correct, a heated object would emit infinite energy at high frequencies, particularly in the ultraviolet region of the spectrum. This absurd result became known as the ultraviolet catastrophe. Not only did it contradict experimental data, but it also violated basic physical intuition. Objects clearly do not release infinite energy, and the universe itself would be unstable if such behavior were real. The failure of classical physics to solve the blackbody radiation problem revealed a fundamental flaw in how energy was understood. Classical theory assumed that energy could vary continuously, taking on any value without restriction. The experimental data, however, hinted at a different reality. Energy seemed to be distributed in a controlled and limited way, following patterns that classical equations could not reproduce. Scientists attempted various fixes. Some modified existing formulas, while others proposed new mechanisms for how matter and radiation interacted. None of these approaches succeeded in fully resolving the problem. Each partial solution either failed at certain wavelengths or relied on assumptions that lacked physical justification. The persistence of the problem suggested that a deeper change in thinking was required. What made the blackbody radiation problem particularly significant was its universality. The radiation pattern did not depend on the material of the object, only on its temperature. This indicated that the issue was not related to the specific properties of matter, but to a fundamental aspect of energy itself. Any successful theory would need to explain this universal behavior, not just fit isolated experiments. The inability of classical physics to address this problem marked a turning point. It showed that even the most successful theories have limits. The blackbody radiation problem was not an isolated anomaly, but a clear signal that the classical description of nature was incomplete. It forced physicists to confront the possibility that energy, at a fundamental level, does not behave in the smooth and continuous way they had long assumed. Ultimately, the Blackbody radiation problem became the gateway to a new understanding of physics. It demonstrated that progress often begins where theories fail, and that contradictions between prediction and observation are not obstacles but opportunities. By revealing the inadequacy of classical ideas, this problem paved the way for a revolutionary concept that would transform science: the quantization of energy. The introduction of energy quanta and Planck's constant marked one of the most profound shifts in the history of science, even though it began as a cautious attempt to solve a narrow problem. When Max Planck confronted the failure of classical physics to explain Blackbody radiation, he did not set out to redefine the nature of energy. His goal was simply to find a mathematical expression that matched experimental results. Yet the assumption he introduced would forever change how scientists understand the physical world. Planck proposed that energy is not exchanged continuously, as classical physics assumed, but in discrete packets. These packets later became known as quanta. According to his idea, the energy emitted or absorbed by matter could only take on specific values, each proportional to the frequency of radiation involved. This was a radical departure from classical thinking, which allowed energy to vary smoothly without restriction. To Planck, this was not a statement about reality itself, but a formal hypothesis designed to make calculations work. Central to this proposal was a new fundamental constant, now called Planck's constant. This constant set the scale at which quantum effects become significant. Its value is extremely small, which explains why quantum behavior is not noticeable in everyday life. In the macroscopic world, energy exchanges involve enormous numbers of quanta, making energy appear continuous. At microscopic scales, however, the discrete nature of energy becomes unavoidable. Planck's constant served as a bridge between theory and experiment. By incorporating it into his radiation formula, Planck achieved perfect agreement with observed data across all wavelengths. This success was undeniable. For the first time, physicists had an equation that accurately described the entire Blackbody radiation spectrum. Yet the meaning of the constant itself remained unclear. It introduced a new scale into physics, one that had no counterpart in classical theory. The idea that nature imposes a minimum unit of action challenged long-standing assumptions. Classical physics had been built on the belief that physical quantities could be divided endlessly. Planck's constant implied a limit to this divisibility. Energy changes below a certain scale simply did not occur. This notion suggested that the universe operates with a kind of granularity, contradicting the smooth, continuous picture that had dominated science for centuries. Initially, many physicists viewed Planck's constant as a mathematical artifact rather than a fundamental feature of nature. Even Planck himself hoped that future developments would remove the need for such an assumption. However, as other phenomena were explained using the same idea, its significance became impossible to ignore. The constant appeared not as a temporary fix, but as a universal property of the physical world. The true power of Planck's constant became evident when Albert Einstein applied it to explain the photoelectric effect. Einstein showed that light itself behaves as if it consists of discrete quanta, later called photons. This interpretation went beyond Planck's original intent and demonstrated that quantization was not limited to matter alone. Energy quantization was a fundamental principle governing the interaction between light and matter. As quantum theory developed, Planck's constant appeared repeatedly in new equations. It defined the allowed energy levels of atoms, the behavior of electrons, and the limits of measurement. Its presence signaled the boundary between classical and quantum descriptions. Whenever Planck's constant could be neglected, classical physics remained accurate. When it could not, quantum effects dominated. The introduction of energy quanta also reshaped scientific methodology. Instead of seeking exact trajectories and continuous flows, physicists began to focus on allowed states and transitions between them. This shift required new mathematical tools and new ways of thinking. Probability and uncertainty, once regarded as signs of incomplete knowledge, became essential components of physical theory. Beyond its scientific impact, Planck's constant altered humanity's philosophical understanding of nature. It suggested that reality is not infinitely divisible, and that there are fundamental limits to how finely physical processes can be resolved. This idea challenged intuitive notions of space, time, and causality, forcing a reconsideration of what it means to understand the universe. What began as a reluctant assumption thus became a cornerstone of modern physics. Planck's constant now appears in nearly every equation describing the microscopic world. It governs the behavior of atoms, molecules, and subatomic particles, and it underlies technologies ranging from lasers to semiconductors. Its introduction marked the moment when physics crossed from the classical age into the quantum era. The story of energy quanta and Planck's constant illustrates how profound change can arise from modest beginnings. A single assumption, made to resolve an experimental puzzle, revealed a deeper structure of reality. In doing so, it transformed physics from a science of continuity into a science of discrete possibilities, forever altering our understanding of the universe. When Max Planck first introduced the idea of energy quanta, the scientific world did not immediately recognize it as a revolutionary breakthrough. Instead, the reaction was cautious, skeptical, and in many cases dismissive. This initial resistance and widespread misunderstanding formed the fifth key stage in the birth of quantum theory. Physicists at the beginning of the 20th century were deeply rooted in classical traditions, and the implications of Planck's proposal challenged assumptions that had shaped scientific thinking for centuries. One reason for the resistance was the way Planck himself presented his idea. He did not claim that energy was fundamentally quantized in nature. Rather, he described his assumption as a mathematical device used to derive a formula that matched experimental data. This modest framing encouraged others to view quantization as a temporary trick, rather than a genuine description of physical reality. As a result, many scientists accepted Planck's radiation law while ignoring or downplaying the conceptual meaning behind it. Classical physics had achieved extraordinary success, and this success created intellectual inertia. Newtonian mechanics and Maxwell's equations had explained a vast range of phenomena with remarkable precision. Engineers, astronomers, and experimental physicists relied on these theories daily. To suggest that their foundations were incomplete felt unnecessary and even irresponsible. Most physicists preferred to believe that the Blackbody radiation problem was a special case that did not threaten the broader framework of classical theory. Another source of misunderstanding came from the radical nature of the idea itself. The notion that energy could be exchanged only in discrete amounts contradicted the deeply held belief in continuity. Continuous change was embedded not only in physical theory, but also in mathematical analysis. Accepting quantization required rethinking concepts such as motion, interaction, and causality. For many scientists, this leap felt unjustified, especially when the idea lacked a clear physical mechanism. The absence of an intuitive picture further fueled skepticism. Classical physics offered visualizable models, particles moving along trajectories, waves spreading smoothly through space. Quantization, by contrast, had no clear physical interpretation at first. It appeared as an abstract rule imposed on calculations, not as a natural consequence of deeper principles. Without a compelling explanation of why energy should be quantized, many physicists regarded the idea as artificial. Even those who recognized the importance of Planck's work often misunderstood its scope. Some believed quantization applied only to oscillators within matter and not to radiation itself. Others thought it was a feature of thermal processes rather than a universal principle. This limited interpretation delayed the realization that Planck's assumption pointed toward a fundamental restructuring of physics. Planck's own reservations contributed to this delay. He continued to search for a classical explanation that would remove the need for quantization. His reluctance to embrace the full implications of his work signaled to others that caution was appropriate. If the originator of the idea did not regard it as fundamental, why should anyone else? The turning point came gradually, through the work of other scientists who extended Planck's assumption beyond its original context. Albert Einstein's explanation of the photoelectric effect demonstrated that light itself behaved as if it were quantized. This result could not be explained within classical wave theory and forced physicists to reconsider the nature of radiation. Einstein's bold interpretation challenged the prevailing belief that quantization was merely a mathematical convenience. Even then, acceptance was far from immediate. Einstein's ideas were controversial, and many physicists resisted them for years. The wave theory of light was deeply entrenched, and abandoning it seemed unthinkable. Yet experimental confirmation accumulated, slowly eroding resistance. As more phenomena were successfully explained using quantization, the idea gained credibility. Misunderstanding also arose from the lack of a unified framework. Early quantum theory consisted of isolated rules and assumptions applied to specific problems. Without a coherent theoretical structure, quantization appeared fragmented and ad hoc. This fragmentation made it easier for critics to dismiss the theory as incomplete or temporary. Over time, however, the practical success of quantum ideas became impossible to ignore. Atomic spectra, specific heat of solids, and chemical bonding all found explanation through quantized energy levels. Each success weakened the argument that quantization was a limited or artificial concept. Gradually, resistance gave way to reluctant acceptance. The initial resistance to Planck's idea highlights an important truth about scientific progress. Revolutionary ideas are rarely recognized as such at the moment of their introduction. They often appear strange, incomplete, or even unnecessary. Understanding develops slowly as evidence accumulates and interpretations mature. In the case of quantum theory, misunderstanding was not a failure but part of the process through which a radically new vision of nature emerged. What began as a misunderstood assumption ultimately became a cornerstone of modern physics. The resistance it faced underscores how deeply scientific theories are tied to human intuition and tradition. Overcoming that resistance required not only new data, but a willingness to rethink the very foundations of reality. Max Planck's lasting legacy extends far beyond his original solution to the Blackbody radiation problem. Although he did not intend to ignite a scientific revolution, his work became the foundation upon which modern physics was built. The seventh keynote focuses on how Planck's ideas reshaped scientific thought, inspired future generations of physicists, and continue to influence both theory and technology in profound ways. Planck's most enduring contribution was the introduction of a new way of thinking about nature at its most fundamental level. By proposing that energy is exchanged in discrete units, he challenged the assumption of continuity that had dominated physics for centuries. This single insight opened the door to quantum theory, a framework that now underlies our understanding of atoms, molecules, and subatomic particles. Without Planck's constant, the behavior of matter and energy at microscopic scales would remain unexplained. One of the most significant aspects of Planck's legacy is how his work influenced other great minds. Albert Einstein used Planck's quantization idea to explain the photoelectric effect, demonstrating that light itself has particle-like properties. Niels Bohr built upon quantum concepts to describe atomic structure, showing that electrons occupy discrete energy levels. Later physicists, including Heisenberg, Schrödinger, and Dirac, developed full quantum mechanics, transforming Planck's initial assumption into a comprehensive and predictive theory. Planck's influence was not limited to theoretical physics. Quantum theory became the basis for technologies that define the modern world. Semiconductors, which power computers and smartphones, rely on quantum principles to control the flow of electrons. Lasers, used in medicine, communication, and industry, operate through quantized energy transitions. Medical imaging techniques such as MRI and advanced spectroscopy depend on quantum behavior at the atomic level. These applications demonstrate that Planck's legacy is not abstract, but deeply practical. Beyond technology, Planck's work changed how science approaches knowledge itself. Quantum theory introduced limits to measurement and prediction, challenging the classical belief that complete certainty is achievable. Concepts such as uncertainty, probability, and wave-particle duality reshaped scientific philosophy. Nature was no longer seen as a perfectly predictable machine, but as a system governed by fundamental limits and statistical laws. This shift altered not only physics, but the broader intellectual culture. Planck also left a lasting institutional and cultural legacy. As a respected academic leader, he supported innovative research and defended groundbreaking ideas when they faced resistance. His support of Einstein during the early, controversial years of relativity and quantum theory helped legitimize new approaches within the scientific community. In recognition of his contributions, leading scientific institutions and awards now bear his name, symbolizing his central role in modern science. What makes Planck's legacy especially powerful is the contrast between his personality and the consequences of his work. He was not a radical thinker seeking to overthrow tradition. He valued order, discipline, and absolute laws. Yet his commitment to evidence forced him to accept conclusions that transformed physics completely. This demonstrates that scientific revolutions can emerge from intellectual honesty rather than rebellion. Planck's ideas continue to shape cutting-edge research. Fields such as quantum computing, quantum cryptography, and quantum communication all trace their foundations back to his constant. Researchers pushing the boundaries of technology and knowledge still rely on the principles that began with his cautious assumption in 1900. Even attempts to unify quantum theory with gravity must confront Planck's scale phenomena, showing how deeply his work is embedded in modern inquiry. In a broader sense, Planck's legacy reminds us that progress often begins quietly. His discovery did not arrive with dramatic claims or sweeping declarations. It emerged from careful analysis and respect for experimental facts, yet its impact was nothing short of revolutionary. The universe revealed by quantum theory is strange, subtle, and profoundly different from classical expectations. Max Planck's lasting legacy lies in the foundation he provided for understanding reality at its most fundamental level. By introducing the quantum concept, he transformed physics from a science of certainty into a science of possibility. His work continues to guide research, inspire innovation, and challenge human understanding, proving that even the quietest breakthroughs can change the world forever.